Bro, phone leads to badness. You go on your phone and everything is slop. Not AI slop, just everything is so lame, dude. Wait, hold on. There we go. And it's like you can find pockets of good, bro. It's like the people that are on the right side, it's like 3 blue, 1 brown. It's like Breaking Taps, Stuff Made Here, Thought Emporium. It's like people that actually do good stuff. They treat themselves with respect. Everyone else, it's like this humiliation ritual of how degraded can we get as a society to just be wrapped up in just the worst stuff. It's just like every time I go on my phone, I go on Twitter, I go on YouTube homepage, I go on Instagram, TikTok, all of them just are just, and maybe it's a reflection of myself, but they're all just so bad, and I always just close it in disgust with whatever I'm being shown. Anyways, what I found though is generally because I've been trying to avoid this Laplace transform thing, honestly, because I don't know it, I have no experience with it, and I'm worried that I'm not going to get it. And what I've found is the best thing I could do, just go live. Because then my mind is like, all right, well, we got to at least read it. We got to read it out loud. We got to understand it. Okay. Okay, so what is this? In general, this seems to be under the category of a symbolic trick to help us get some answers. In this chapter, we study an analytic technique for finding formulas for solutions of certain differential equations using an operation called the Laplace transform. This technique is particularly effective on linear, constant coefficient equations and is quite different from our previous methods. The Laplace transform lets us replace the operations of integration and differentiation with algebraic computations. As a technique for solving initial value problems, the Laplace transform is sometimes more and sometimes less efficient than our previous techniques. The importance of the Laplace transform is that it is useful in several different types of applications. For example, the Laplace transform lets us deal efficiently with linear, constant coefficient differential equations. That have discontinuous forcing functions. These discontinuities include simple jumps that model the action of a switch. Using Laplace transforms, we can also make a meaningful mathematical model of the impulse force provided by a hammer blow or an explosion. Okay, I don't really know what that means, but the modeling of a switch part makes sense. Laplace transforms also find solutions for a forced harmonic oscillator or using solutions generated by a completely different forcing term. Wait, what? Laplace transforms also find solutions for a forced harmonic oscillator using solutions generated by a completely different forcing term. I don't know what that means, but we'll figure that out. By the way, guys, I'm thinking after the class is over, I'm probably going to continue with these books, hopefully. I mean, chapter 4 looks really interesting. Chapter 5 looks super interesting. And chapter 8 looks interesting. I'm probably not going to do any numerical stuff. But I would like to say that I've finished 2 books of mathematics, on my stream. Okay. Laplace transforms also find solutions for a forced harmonic oscillator using solutions completely different. This technique is useful when working with a system that is modeled by an unknown linear constant coefficient differential equation for which we provide the forcing function. Okay, so I guess they're really talking about forcing. Laplace transforms give us a way of extending our qualitative analysis of homogeneous linear equations using eigenvalues to non-homogeneous linear equations. Okay, that is the sentence that I wanted the most of. That's good. Because my question when reading that whole paragraph was, we already know about, linear systems, their eigenvalues and whatnot, but we don't have non-homogeneous. That's only homogeneous linear equations. Okay. In this chapter, we study a tool, the Laplace transform, for solving differential equations. The Laplace transform is one of many different types of integral transforms. In general, integral transforms address the question, how much is a given function y of t like a particular standard function? For example, if y of t represents a radio signal, we might want to compare it to the function sine omega t, a sine wave with frequency omega over 2 pi. By adjusting the parameter omega, we could test how well y of t fits sine waves with different frequencies. Ideally, for each value of omega, we would like a number that indicates how much y of t is like sine omega t. One way to accomplish this comparison is to compute the integral minus n to n of y of t times sine omega t dt. If y of t is oscillating with frequency omega over 2 pi and is positive when sine omega t is positive, then this integral is very large. If it has some other frequency, then the signs differ at some time, so there's cancellation in the integral and it's smaller. To use this idea in differential equations, it's natural to compare y of t to the function that comes up most often, the exponential function. In fact, we could use the complex exponential and compute the integral from minus infinity to infinity of y of t times e to the minus zt dt. Where z is complex. The larger the value of this integral for a particular z, the more y of t is like but why do they have a minus here and not a minus there? In particular, if y of t is equal to e to the zt, then the integrand oh. That's why. In practice, it turns out to be easier to write z in terms of its real and imaginary parts, as z Okay, so you compute two integral transforms separately. And this second one is called the Fourier transform of the function y of t. And its value at a particular value of omega is a measure of the extent to which y of t is oscillating with frequency omega over 2 pi. The imaginary part of this quantity is the comparison of y of t. Wait, what? Yeah, to sine omega t, as discussed above, and the real part is the comparison of y of t to cos omega t. Although the Fourier transform has many important applications in differential equations, it is not discussed in this chapter. Rather, we focus on the integral for S is real, right? Yeah, S is real. Okay, so what did we just learn? What integral transforms kind of do. And then this thing, I can already start to see why maybe this thing is good for linear. Because when it's nonlinear, this thing is, I mean, how do you know that it's going to be similar to this? But what we've seen so far is that e to the I, or e to the zt is like, kind of describes the behavior of linear systems. Because, I mean, pretty much everything we saw in chapter 3 can be described in terms of e to the zt. Okay, so that's actually pretty cool. The Laplace transform of a given function y of t uses integration to compare y of t to the exponential functions e to the st. The Laplace transform function y of the function little y is defined by y of s integral from 0 to infinity of y of little y of t e to the minus st dt. I'm gonna go get some more water. I'm out of water, bro. You know we stay hydrated up on this stream. Okay, all right. Let's get back into it. The Laplace transform of a given function uses integration. Oh, yeah. Okay, wait. So let me just start writing some notes. Y of s is equal to the integral from 0 to infinity of y of t e to the minus st dt. Now, one thing that I want to do check, though, is that they said... So why don't we use the complex one? So did this come out after, just out of curiosity, did this come out after the Fourier transform was made? Or I don't know. Okay. All right, example. We have little y of t is equal to e to the 2t. Then big Y of t is equal to the integral from 0 to infinity of e to the 2t. But then times e to the minus st dt, which is equal to the integral of e to the 2 minus s t dt. Okay. Wait, what is this here? If s is 2, and this goes to 0, so then e to the 0 is 1, so the limit is 1. Oh, but it's undefined. It's undefined at... So, but I don't understand this step. Oh, guys, check this out. This is so cool. Okay, crows are really cool animals. They're so much like us, man. First off, they do lifelong... Look, they form lifelong pair bonds. Isn't that crazy, man? Dude, crows are so cool. I mean, the crows piss me off because they're so annoying, but Oh, right. Okay. So they just took the integral. I was just messing that up. They just took the integral. So they converted the, what is it called? Improper integral? Indefinite? What did they call it? Improper. To a limit. Then they computed the integral, because now this is like chill, but we still have the limit. And then we evaluate, so then we have for t, right? So this is going to be b minus e to the 0. Wait. Oh yeah, they factor this out. They still have the limit as b goes to infinity, and then you get this thing. So that's the Laplace transform? But what does it mean? Okay, let me write these steps out just because this is all new to me. Okay, so then we need to convert improper integral. So then we do is equal to lim b goes to infinity, the integral of 0 to b of e to the 2 minus s t dt. Okay, and then we actually do know how to take this integral. So then if we have the integral evaluate integral, so e to the a t dt is equal to 1 over a e to the a t. I guess before this quiz, I'm going to need a refresher on all my integrals, because we did that earlier, but, you know, I got to do that space repetition. Okay, so then we're going to get this step. So we're going to get is equal to the limit as b goes to infinity of 1 over 2 minus s times e to the 2 minus s t evaluated at b and 0. So now we evaluate definite integral. And we're going to get this step. So it's going to be, you know, it's equal to lim as b goes to infinity of of 1 over 2 minus s times e to the 2 minus s b minus 1 over 2 minus s e to the 0, which is equal to 1 over 2 minus s times the limit as b goes to infinity of e to the 2 minus s b minus 1, right? E to the 0 is minus 1. Wait. If s is greater than 2, this is negative, and then this goes to 0, so then the actual value is this. Okay. So then we get that the Laplace transform of... What do you say? What are you supposed to say verbally? I don't know. In other words, the Laplace transform for the function... Oh, okay, that's what you say. The Laplace transform function y of s for the function y of t is equal to e to the 2t is... What does that even mean? I don't know what that means. What does that tell us? This computation involves a number of technical details with improper integrals that are important, but don't let them to cause you to lose touch with the underlying idea involved in the definition. The Laplace transform associated to little y of t is a function that measures how close y of t is to the exponential function e to the st for values of s. Hey, wait. How come this became s minus 2? It should be 2 minus s, right? How did that change around? It comes simply from two facts. Oh, wait. Oh, so that first part good. Okay, so it's actually trickier than I even thought. So oh, cool. Okay, so what happens is you get b so if s is greater than 2, then the first term in the definite integral evaluation goes to 0. So we're left with minus 1 over 2 minus s, which is equal to 1 over s minus 2, equal to y of s, if s greater than 2. But if it's not, what is it? It's undefined. If s is less than or equal to 2, then y of s undefined. Okay. So if s is y of s tells you how close y of t is to the exponential function e to the st for functions for values of s. In this example, we found the Laplace transform of e to the 2t is a function y of s that is very small if s is much larger than 2, but as s approaches 2, the values of y of s increase until they become unbounded at 2. Surprisingly, we can use this idea to solve differential equations. That is surprising. I don't understand that. Let's see. As we will soon see. But we can use the Laplace transform to convert a differential equation into an algebraic equation, which is often easier to solve. This conversion is similar to the translation of an English sentence into a sentence in Chinese. Both sentences have the same meaning, but the words and grammar are very different. Y of t represents a phenomenon in terms of the independent variable t in the time domain, and the function y of s represents the same phenomenon in the s domain. More formally, we say that the Laplace transform defines a mathematical transformation that takes a function y of t into a transformed function y of s. From a strict mathematical point of view, this transform is just one particularly nice function that converts a function into a new function. We'll use the script letter L to represent this function. In other words, we say that y is equal to L of y. Okay, so notation. We have little y of t goes to big Y of s under the action of L. So then we say L of y with brackets is equal to big Y. And then we would say, example, curly L of e to the 2t is equal to 1 over s minus 2 for s greater than 2. This way of writing the Laplace transform is somewhat sloppy in that it assumes the independent variable of the transform function is the variable s. Yeah, not a pure function. Bro, these mathematicians don't even know about pure functions, bro. All right. In that it assumes the independent variable but this hardly causes any confusion. Yeah, why would it? All right, in order to be certain that the Laplace transform exists, that is, the improper integral converges for at least some values of s, we must restrict attention to continuous or piecewise continuous functions for which there are, okay, so restrictions on little y of t. Continuous or piecewise continuous? Okay, so in bounded time, so there for which there are positive constants k and m that such that the absolute value of y of t is less than Okay, so continuous or piecewise continuous and what is it called? No more than exponential growth. As a practical matter, most functions encountered in applications have this property. I think it's probably because the integral blows up, right? Also note that the Laplace transform is defined as an integral over the interval 0 to infinity rather than the entire real line. If the Laplace transform were to be evaluated over the entire real line, then the restrictions on the function y of t in order to ensure convergence it would be much more stringent. Okay. Computation of Laplace transforms of exponential functions. Okay, so far this is actually going pretty well. I'm not like too scared, you know. For function y of t and a given number s, the value of the Laplace transform at s measures the degree to which the function y of t resembles the function e to the st. Yeah, it'll be interesting to see how the differential equations come into this thing. You know, when you're scared of a new topic like this, you got to have an open mind because it really is actually super weird in a good way. To check this assertion, we compute the Laplace transform from an arbitrary exponential function. Then we get the same thing. We do this thing. We do this thing, and we get this thing. Cool. If s is less than or equal to a, then the improper integral diverges. Strictly speaking, the Laplace transform of e to the at is the rational function 1 over s minus a restricted to the interval s greater than a. Note that our earlier calculation of Laplace of e to the 2t was simply a special case of this calculation. There is another special case of this computation that is worth... Bro. Alright. There's another special case of this computation that is worth mentioning at this point. If a is equal to 0, then e to the at is equal to 1 for all t. Consequently, we have also computed the Laplace transform for the function that is constantly 1. Since a of 0 equals 0, we have L of 1 is equal to 1 over s for s greater than 0. So what does that say? That says that the 0 is kind of the thing that's most like our little y. We often need the results of these computations as well as the transforms of other frequently encountered functions. Therefore, we provide a table of the Laplace transforms as well as a list of important properties of this transformation on page 626. Okay, properties of the Laplace transform. Okay, properties of L. There are many transforms that convert one function into another, but the Laplace transform has one very special property that is the basis for its success in solving differential equations. Laplace transform of derivatives. Given a function y of t with Laplace transform L of y, the Laplace transform, okay, so 1. Given y of t with L of y, then L of dy dt is equal to S of L of y minus y of 0. Okay. But why? Oh, here we go. To verify this theorem, we use the definition of L of dy dt. And we... Okay, so to check, expand L of y prime is equal to the integral from 0 to infinity of dy dt times e to the st or minus st dt. And integrate by parts. Yeah, so I'm definitely going to need to do review, at least a couple hours of review. What book is this? It's in the title of the video, guys. This should be first year university. If you're doing differential equations, it's a first year. But the book title is in the video title, okay? All right. So yeah, integration by parts. We're definitely gonna have to review that. So we take u equal to e to the minus st. Okay, first let's remember the integration by parts is like the reverse of the product rule. So it's like you have some product rule and you integrate that and you get u times v. So if we have u prime v is equal to so let's start out with uv is equal to u prime v plus v prime u, but then we get u prime v is equal to uv minus oh wait, the integral. Okay, the integral of it. Hold on. Let's just do a like a really fast thing here. Right. Yes. Right, because if you move this to the other side, you get u v prime plus v u prime and the integral. And the integral of all that is just going to be u v. So we're trying to find this. And so we need to find the integral of right. And then you use the differentials to expand it. Okay. All right. We'll do more review later, but that's the quick part. Right. And then we take dv. And we take u equal to e to the st and dv equal or dv dt equal to dy dt. So that means that dv equals dy over dt times dt, but then they cancel, right? Du dt, okay, that's easy. And then we integrate this thing, and we just get v is equal to y. Doesn't this cancel, and then you just get dy, and then that's y? Okay, so this is the uv part. But I don't know why there's an integral in here. Or I mean, I don't know why there's this. What is this? Because uv typically doesn't have this limit in it. Okay, and then this becomes. Oh, and then, but this is cool because this becomes. You can take this. No, you can't take this s out. Wait, can you take that s out? So this is. V, and then this is du. It does for definite integrals. Yeah, you can just take s out. That's what, because it's not an integration variable. It's just a value. So then this becomes L of whatever. Yeah, that's what I thought. Okay, that's what I thought. Sometimes I just need to read ahead. So this part becomes y of t e to the minus s b minus e to the 0. So this is going to be y of t times e to the minus sb, and this is still limit b goes to infinity, minus y of t, because the other thing just goes to 1, right? 0, 0, 1. Okay. So then, but if b goes to infinity, then that first part goes to 0. Our earlier assumption that y of t has at most exponential growth is important here. Since the absolute value of y of t is less than e to the mt for some constant m, I don't understand this one. Why? It's just some constant m. S could be negative, right? Could s not be negative? Because if s is negative, then this limit is not 0. Oh, interesting. Wait, actually, I missed that this also becomes y of b. This becomes y of b, and the other one becomes y of 0. Okay, so then then apparently this goes out and dies, and you just get L of dy dt is equal to minus y of 0 plus s L of y. Okay. And then we finally have this. That's actually very beautiful. I like that. S greater than M works. All right, we'll need to do some practice exercises and come back to it a few times. This formula is the fundamental property of the Laplace transform that lets us essentially replace the calculus operation of differentiation in the time domain with the algebraic operation of multiplication by s in the s domain. Of course, this description is not quite right because we also need to remember to subtract y0. But in any case, we think of the Laplace transform as an operation that turns a problem in calculus into a problem of algebra. Turning a problem in differential equations into a problem in algebra would not be very useful if the Laplace transform did not have reasonable algebraic properties. However, due to the definition in terms of an integral, the Laplace transform has nice linearity properties. All right, can we think about that? The integral is already a... so this is the definition. Where's the definition? This is the definition. So if we give it two functions, or if we have a function f and a function g, then the Laplace transform of f plus g Okay, let's just hop on the camera and I'll see if we can try to figure that out. I'm pretty sure they show it, but I want to show it too. I like showing my overhead camera. I feel like this thing is slid down. I guess it hasn't, but it's too big. All right, so what they're trying to say is that the L of f plus g, where like f of t, g of t, is equal to the Laplace transform of f plus the Laplace transform of g. And it's and so just to remember the definition, so this is 6.1 DE, that L of y is equal to the integral from 0 to infinity of y of t e to the minus st dt. This is just the definition. So then if we say that like f plus g is equal to h of t, then we get L of h is equal to the integral from 0 to infinity of f of t plus g of t times e to the minus st. Verifying linearity things is always so easy, but so this is going to distribute out. We're going to get integral of 0 to infinity of f of t e to the minus st plus g of t e to the minus st dt And then since integrals are linear, this just becomes integral of f e minus st plus integral dt plus integral of g of t e to the minus st. And since the integral of kf is equal to the k times the integral of f, therefore the Laplace transform is a linear map. So the Laplace, therefore, L is a linear transformation. All right, so that's the proof of that. I love verifying linearity because it's like not that hard, but it also makes you feel like you understand it. So they did the exact same thing that we did, but we did it first. All right. I didn't even need to see the proof. All right. Solving differential equations using the Laplace transform. All right. Solving DEs. Consider y prime is equal to y minus 4e to the minus t with y of 0 equal to 1. We first study this problem using qualitative techniques so that we know what to expect for the analytic form of the solution. What does that even mean? Oh, yeah. Okay. So let's just think about it. Sometimes they say it's so fancy. Why not just say, hey, look at it, think about it. Why not just think about it? So this thing, when t goes to infinity, it goes to 0. So this whole thing's going to go to 0. But y, it depends on the initial condition. So y is, so our initial rate of change is going to be, so no matter what, this thing goes to 0. So then we're probably just going to get we're probably just going to get ce to the t. Because this is really the only part that matters when this goes to infinity. So it should just look like a... Okay, I guess I did it wrong. Oh, no, wait. Wait. Hence, we expect the solution to be... Oh, but you know what? When this is 0... Oh, but it starts off negative. Oh, interesting. So you can't just disregard that part of the term. It indicates that the solution decreases for t near 0. Once the solution crosses below 0, oh, that's very interesting, man. Both terms on the right-hand side are negative, so then the solution just exponentially decreases. Okay, so my qualitative interpretation was wrong. Guys, I don't know how I can say this more. Read the video title. I don't know if you're on mobile or what. If you read the video title, the textbook name is in there. It's Differential Equations by Blanchard. Okay, not to be rude, but it's like the number one question I get, and I put it in the title every time. So it's just kind of funny that people always ask me that. Plus, it's also up at the top here. Anyways, you can Google it and you can find a free PDF, or at least I did. I found a PDF. All right, solution using Laplace transform. This equation is linear, but it's linear non-homogeneous, which is my least favorite type of linear differential equation. Okay, this equation is linear, so we could use the techniques of 1.8 or 1.9. However, the Laplace transform provides an alternate method of solution. Starting with the IVP, the first step is to take the Laplace transform of both sides. Okay, then using the previous formula for the Laplace transform of a derivative to simplify the left-hand side and the linearity principle of the Laplace transform on the right-hand side, we obtain this. All of this is actually not as complicated as I thought. Hey, bro, that's sick that you're a math PhD, man. That's cool. Where you go? What are you studying now? That's cool, bro. I like complexity theory. I like combinatorics. I've always liked combinatorics. Combinatorics is a great field. I love counting. I've always liked counting. You know, it's like 1, 2, 3. What's after that? You know, who knows? Anyways, okay, so we substitute in the initial condition. Let me write out these steps. Okay, so we have a differential equation. So 1, get a differential equation. I guess a linear differential equation, is it only for linear? Let's specify linear. So our example is this one. 2, apply L to both sides. Okay? Substitute in for y of 0. Number theory. Oh, dude, partitions are so sick. Yo, okay. Hey, so wait, hold on. Oh, really? Wait, dude, that's sick. Okay, I actually have a use case for fast partitions. So I found let me see. I forget what my number is, but I found a sequence so there's Landau's. So there's Landau's, which tells you for the symmetric group what is the group element with the highest order. And I found that I don't remember what my number is. I have a sequence in here. Actually, if I just look up. Okay, here's my sequence. So I have 3 sequences. Or I have. Wait, what is the difference between these? Okay. I commented on this one, but I have 3 of my own sequences. But anyways, the point is I use partitions of integer sets to figure out what the maximum number of cycles in any partition of Sn is of highest order. So like, because the least common multiple, if you take some partition of the integers from 1 to n, and you take the least common multiples of their lengths, then you'll get that group order. If you take all of the group orders of every partition for a given n, then you'll get, a list of least common multiples. If you find all of them with the highest least common multiple, but there's a variety of them. There isn't only one that satisfies Landau's function or whatever. So anyways, but the thing is, I only calculated like 25 because it was a little slow to compute partitions. So if you have fast partitions, bro, show me the way. Because I'm in need of some fast partitions, bro. All right. um. Oh, I see how this is an algebraic operation now. Hold on, I'll be back in a second. Okay, I'm back. I am back. Use Sage. Yeah. Rademakers. Oh, yeah? I feel like I've heard of that, actually. Partitions. Okay, I'll look into this later. I got a ton of work to do. But that's sweet. It's very cool. You can easily go to 10 to the 7? Wait, does that mean like the underlying set is that size, or it's like that is Flint? You don't want to implement it yourself. I can imagine. Bro, I was just watching this thing about how they computed the 8th Dedekind number, and man, some of this stuff just to find these sequence elements is like incredibly challenging. All right, let's lock in. I could talk to you all day, bro, but we got homework due. We got the crushing weight of reality and real life on my shoulders right now, and it's just time to lock in. Okay, so then the next step is you do this, then you evaluate. Okay, so you're given this differential equation. You don't necessarily know what L of y is. So you're trying to solve for L of y. Right? Okay, so then the next step is to evaluate all the known Laplace L's. And okay, so the next step after that is the unknown. Okay, the unknown of the original differential equation is the function y. So we solve this equation for the Laplace transform of y. Okay, so then 5, solve for L of y. These calculations yield the Laplace transform of the solution of the initial value problem. Note that we used only arithmetic to obtain L of y. The calculus is hidden in the computation of the Laplace transform of exponentials. In a certain sense, we have now solved the IVP. Unfortunately, we're not looking for the Laplace transform of y. We're looking for the actual y. So we must undo or take an inverse Laplace transform. Okay, so then 6 will be inverse Laplace. Okay, so it's inverse L. To use Laplace transforms, same. All right, see ya, bro. Dude, that guy was cool as hell, man. Partitions? I love partitions. All right. To use Laplace transforms to solve a differential equation, we first compute the Laplace transform of both sides, then we solve for the Laplace transform of the solution. And then to find the solution, we find a function with the given Laplace transform. The last step is called taking the inverse Laplace transform. The notation for this is L inverse. Okay, so notation L inverse. Okay, and so one thing that we should consider is that we already proved that I think it would be on the I mean, the conditions are slightly tighter because you need that bounded. You need that it grows slower than. It grows slower than some exponential or something, so it doesn't grow super exponential or whatever. But the point that I'm trying to make is that on the piecewise continuous real valued functions, I don't know if it has to be even real valued, but we have a linear transformation. And so the existence that this is an invertible linear transformation is not obvious, right? Because at least to me, it's not obvious that this is an invertible linear transformation. So let's just say, on what domain is the Laplace transform a linear map? Because it has to be invertible. It's got to be invertible. Right. So, okay. So it's all piecewise continuous of exponential order. That's how you say it in math language. Okay. So then how do we show it must be invertible? Linear. Or is it? Okay. Domain is a linear map. The vector space of functions on 0 to infinity of exponential order. And then the codomain is the vector space of analytic functions on the corresponding region of convergence. Whoa. Okay, so that's a little more advanced than maybe I was. I mean, I was expecting it to be advanced, but needless to say, there's like a formal thing that okay, it indeed is a invertible linear map. But if that's the case, so does it have eigenvalues and eigenvectors? It's an infinite dimensional vector space, but the eigenvalues and the eigenvectors. All right, let's just keep going. All right, so anyways, we have an if and only if though. So they just tell us there's a uniqueness property for inverse Laplace transforms which state that if f is a continuous function with L of f equal to big F, then little f is the only continuous function whose Laplace transform is f. This uniqueness property allows us to say the inverse Laplace transform of f instead of an inverse Laplace transform of f. Okay, but yeah, I'm guessing my book does not get into that. Okay, so because it's a linear operator, we have this. Therefore, okay, fine. So now the things to note is that we have if L of f equals big F, then if and only if L inverse of big F equals little f, and L inverse is linear. So L inverse of, AF plus BG is equal to this is big F and big G, is A L inverse of big F plus B L inverse of big G. Okay, cool. Which, Linearity is important because it allows us to compute the inverse Laplace transform of a complicated sum by computing the inverse Laplace transform of each summand. Inverse Laplace transforms are generally computed in much of the same way as antiderivatives in calculus are computed. We work with a small list of known transforms, and to compute the inverse Laplace transform of a complicated function f of s, we first break it into a sum of functions. All right, so I imagine we'll have to do some partial fraction decomposition or something weird. I knew it, bro. I knew it. Why wouldn't you do that? That's pretty cool, though. All right, so we'll probably have to practice some partial fractions in a little bit. Okay, wait. So, all right. So yeah. So partial fractions will be. All right. So let's do an example. When we applied the Laplace transform to the IVP earlier in the section, we arrived at this expression. All right. Then they show that. This is the inverse Laplace transform of this, but they didn't tell us the whole thing, right? We have, so it's going to be, so then our final solution to that differential equation is e to the t plus 2e to the, oh, because there was this one and that one. Okay, that's fine. Completion of the IVP. Oh, here we go. So we did this, and we compute the, then we split it up, then we, okay, there we go. Nice, that was easy. This is actually not that complicated. I feel like I'll be regretting my words in a minute, but it's actually not so hard. All right, let's work with a better example. The RC circuit. Consider the RC circuit here. We let V of C be the voltage across the capacitor at time t. R is the resistance, C is the capacitance, and V of t is the voltage supplied by the voltage source. From electric circuit theory, we know that the voltage satisfies the differential equation. Bro, how many times I've written this down and I always forget it? I just always forget that. Suppose the voltage source V of t has constant value 3, and the initial voltage across the capacitor is 4. With the quantities R equal to 2 and C equal to 1 as in figure 2. Okay, so we get the IVP. Solve for dV dt. Oh yeah, so we should look at this. Make sure that this is, it's autonomous, but it's linear, non-homogeneous. Yeah, it's autonomous, meaning that there's no t in here. Hence the solution. So this is greater than 0, and this is 4, but this is going to just go to 0. Or it's going to go to 3/2. Or wait. No, it's going to go to 3. Okay. So it's separable and linear. Honestly, yeah, it would be so much easier to integrate this, would it not? Maybe not. I don't know. So that was one step that maybe I should walk through, is in this example, how they did this. So they So they had S of L of y minus 1 minus L of y is equal to minus 4 over s plus 1. We can move the 1 over, so this is plus 1. So then we get SLY minus LY is equal to minus 4 over s plus 1 plus 1. So then we can factor the L of y times s minus 1. Oh, and there we go. Okay, cool. So that was just a little bit of algebra to double check. Okay, so then we do more of this, more of that, a little of this, a little of that. Move this over, move that over, factor the L. Symbolically, it's not that hard. Yeah. I was getting worked up over nothing. This whole day I was like, oh shit, I'm going to have to learn Laplace transforms, but it's actually not so hard. Okay, to compute the inverse Laplace transform, we use partial fraction decomposition again. Hold on. Wait. What is going on here? So we're going to get 4 over s plus 1 half plus 3 halves 1 over s times s plus 1 half. So this makes sense. Oh, because they don't need to do partial fraction decomposition on this, so they only did it on this one. Okay, so I understand. They only on the one that's non-elementary. So they don't even show how to do it. They just tell you, okay, here's the partial fraction. And so now we have our true form of the Laplace transform for our voltage. And then we need to compute the inverse Laplace transform for both. Wait, hold on. 3 over s. Oh, did this cancel with that? Okay, this canceled with that. All right, we're on to the exercises. Let's freaking go, boys. Let's go. All right, so it's time to do some real problems. Because, you can think you know it, but you don't because you didn't do any of the problems. That's just how it is. Okay, so we need to compute for f of t is equal to 3, L of f. All right. So here we go. So I always mess with these. I always mess these up, but L of f is equal to the integral from 0 to infinity of 3, because f of t is 3, e to the minus st dt. Now we don't even need to use integration by parts for this. So in this case, this is equal to 3 integral 0 infinity e to the minus st. And I believe that this should be equal to, so first off we need to do this thing with the limit as b goes to infinity of integral of 0 to b e to the minus st dt. And then we turn this integral into 1 minus 1 over s e to the minus st, evaluated from b to 0, limit as b goes to infinity. Okay, we're getting somewhere. So now what do we do? So this is going to be equal to 3 lim b, okay, and this is going to be minus e to the minus st b over s minus, and this is going to be 0, so this is going to go to 1. So this is going to be minus 1 over s, so plus 1 over s. And this is still lim as b goes to infinity. And so this should be equal to 3 lim b infinity, or 3 over s. We can do this, 3 over s times 1 minus e to the minus sb. Now, I don't know if I did this right, because what am I supposed to do here? Because is s required to be positive? I think we just say that. I think we just say that unless if s is less than 0, then this thing is going to be positive, and then this expression goes to infinity. So we need that s is greater than 0. So we need that. Right? And then and if that's the case, then if that minus e to the minus sb goes to 0, so then we should just get 3 over s is equal to L of f. Let's double check our answer, because I don't even know if that's right. So we need to go down to 6.1. Dude, I actually love Laplace transforms. They're cool. 3 over s, boys. I am goated at Laplace already. How long have we been doing this? Only an hour 30. Feel pretty good, not gonna lie. It's not so hard. What's up, Lucky Seer? All right. Yeah, guys, I did the easiest possible Laplace transform, and I'm all up on my high horse. All right, let's do. I think we should just do. Let's do problem 3. Okay, so problem 3. H of t is equal to minus 5 t squared. Find L of h, the Laplace transform. Okay, so we just get to it. We just expand the definition. So L of h is equal to the integral from 0 to infinity of minus 5 t squared e to the minus st dt. All right, this is going to be equal to, so let's just do our expansions, minus 5. So wait, is this, okay, so now, now we ran into something where we need to do integration by parts, because we're going to have to evaluate this integral. And so the typical way you do this is you pick, so okay, wait, hold on. So uv is equal to the integral of u prime v plus v prime u. So this is just the product rule. But what you want to do is this is equal to the integral of u prime v plus the integral of v prime u. And so I think typically what you do is you pick this side, so then you end up with, or you pick this side. So you get u dv is equal to uv minus the integral of v du. Okay, this is the integration by parts formula. Okay, but that doesn't really help you because you have to pick, I think you pick u equal to this. So we can say u is equal to e to the minus st. And then we pick dv dt equal to t squared. I think that I picked wrong, but we will see. Because we're going to integrate this, and we're going to get like t cubed over 3. And then this is going to be, but then you're going to get like t cubed over 3 times du, which is going to be like minus se. Am I in frame? Laplace transforms, bro. Okay, so se to the minus st, but then you're going to have to take this integral. So this is not a good choice for our integration by parts, I think, because then we're just going to keep going up and up and up. So instead, if we picked u equal to t squared, then du dt is equal to 2t, and we'll pick dv equal to, or we'll pick dv, hold on, we'll pick dv dt equal to, or we'll pick dv equal to e to the minus st dt. Okay, so now let's see what does this shake out to be. So this shakes out to be that the integral of u, which we're not choosing this one and we're not choosing this one because that one was a bad choice, is going to be t squared dv e to the minus st dt. So this is this left-hand side, which is equal to the integral that we have to take. So that's good. But this is going to be equal to uv. So now we have to figure out what this is. So we need to take this integral. So we're going to get the, I'll just write it down here. The integral of dv is equal to the integral of e to the minus st dt, which should be equal to minus e to the minus st over s, right? I think so. Oh, shoot. I need to actually make my, I typically make my, here, let's just do it. Hold on. Give me 1 second. Okay. All right. So now I have a little bit more room to work with. Focal length 70 millimeters or something like that. All right. Okay, so this is our V. So this is V. So now we get UV. So U is t squared, or minus t squared e to the minus st over s, minus the integral of v du. So v is, so we can just change this to a plus, I guess. And we get e to the minus st, or 1 over s. And this is going to be du. So du is equal to 2t dt. So then do you have to do a second round of... Do you have to do a second round? See ya, bro. Do you have to do a second round of this? I don't even know. Because I don't want to do... When you have to do 2 of them, it's so confusing. But I'm pretty sure you do. And that's why they had us do this one. So we should have done 2 before we did 3. All right, so let's... I'm pretty sure that that you do. That you have to do 2 rounds of integration by parts. But one knows. But one knows. No, do it the long way. But one knows. Indeed, one does know. Okay, so yeah, so I was right. You have to do 2 integration by parts, and then you get the thing. That is pretty tricky, man. That is pretty tricky. Okay. Ooh, problem 5 seems kind of fun. Ooh, 6 seems fun. Dude, what's cool about these exercises though, when you read a book instead of just watching a video, or like even like, because let's be honest, if you're watching this, you're probably not learning anything. You have to actually be doing it. But what I love about problems like this is that you feel like you're inventing it yourself. You feel like, okay, I could have done this. Okay, find inverse Laplace transform. Compute the Laplace transform, substitute, and solve. Okay, so then just a bunch of IVP solves. But please use the method of Laplace transforms. Ooh. Okay, so let me just write down some problems that I want to do. I'm supposed to read 6.2, so I don't know how far we're gonna get with this, because it's already 4 p.m. and I have 2 homeworks to write up. So, but problems that I definitely want to do are, let's do 2, just so that we get the hang of it. For now, I'll do it on the weekend during my review streams. We'll do 6, 5, and 6, because those are really cool. But let's do 7, 8, and 9. So we're gonna do 2, 7, 8, 9. Then we're gonna compute some IVPs. So we're gonna do 15, 16, 17. We're gonna try to do, what is that? That's 7 exercises. 26 is really good, but we're not going to do 26. All of the examples in this section and all of the differential equations in this exercise set are linear. Trying to use the Laplace transform on even the simplest nonlinear. Ooh, bro. Oh, we have to do 27. 27 is rad. Okay, I'll be back in a sec. Okay. All right. We got some problems to do, and all right. So 2, 7, 8, 9, 15. All right. We read through them. Dude, I really think I'm gonna get a new microphone. All right. We're doing problem 2, which is going to be only one integration by parts. So 2, find L of t. This is going to be equal to the integral from 0 to infinity of t e to the minus st dt. Don't test me, bro. Don't test me. All right. So now we're going to have to do integration by parts. So remember, let's just do this thing again, because the more I do it, the easier it becomes. We're going to get uv is equal to the integral of uv prime plus integral of vu prime. Then I think, I don't know, but convention, I'm pretty sure we picked this one. So we say integral of uv prime is equal to uv minus integral of v du. This is dv. Okay, so now that we have set up our thing, we just need to pick which one we want. So we want u to be t, I think. So we're going to say u is equal to t, because then when we take this integral, because we're not going to take this integral, right? We're just saying that by the definition of the product rule so we're not going to actually take this one. The only integral we have to take is this one, and we have to integrate dv. So then we're going to say u is equal to t, and dv is equal to e to the minus st dt. So now what we're going to do is du equals dt, and then we're going to integrate both sides. We're going to get v is equal to the integral of e to the minus st dt, which is equal to minus e to the minus st over s. Now we're ready to actually set up the answer. Which is going to be, so now we're going to get, so uv is equal to, okay, so all right, so we're going to get, why am I freezing up? It's going to be a uv, which is t times minus e to the minus st over s minus the integral of v, or wait, is that right? E to the minus st times du, which is dt. So I think this is right, and this is going to be equal to, so this is plus e to the minus st over s. So we should be able to factor this out into, so this is going to be a plus, this is going to be a minus, so then we can do e to the minus st over s times 1 minus t, right? So this is the integral. So this is equal to the this is equal to this integral. So these are the same. Now we're going to take this and it's going to become a limit. B goes to infinity of e to the minus st over s, 1 minus t, evaluated b and 0. Now this becomes let's just write it all out. E to the minus sb over s times 1 minus b minus, this is going to be e to the 0, which is 1. So this is going to be 1 over s times 1. Okay. Now, this still has this limit as b goes to infinity. So to compute that, if s is, let's see here. Let's expand this, actually. So we're going to get e to the minus sb over s minus be to the minus sb over s. So this term, if s is greater than 0, then this goes to 0. And this should also go to 0 because this is going to go to 0 way faster than... Actually, is that true? I don't know what to do about this term. Okay, so wait, hold on. So we're trying to evaluate the limit as b goes to infinity of minus b e to the minus sb over s. Let's ask ChatGPT. I don't know what the answer is. Bro, I'm so dumb. I knew it was going to be L'Hopital's rule. Okay, so yeah, you got to use L'Hopital's rule. So we can equal this is going to be 1 over s lim b goes to infinity of minus, or let's do minus 1. So this is going to be b over e to the sb. If we apply L'Hopital's, the hospital's theorem, then we get 1 over s e to the sb. So the limit is 0. So nice. So these both go to 0, right? So then shouldn't L of t be 1 over s? But what did we get for the last problem? Hold on. We got 3 over s for 3. So I feel like I did something wrong, because how could t also be 1 over s? Wait. Hold on. Hold your freaking horses. Thanks, Gab. E to the minus sb over s minus... Then this is going to be... So here we've evaluated it. So shouldn't it be minus 1 over s anyways? Okay, that's my guess. Let's check the answer. Because I feel like I missed something and I don't know what I missed. Calculate Laplace L of t. Okay, so we do the integration by parts. We took u as t, took dv as e to the minus st. Okay, perfect. Okay, we computed this integral properly. The boundary term? What is the boundary term? That's when t is 0. Okay, so they started with the boundary term. Wait, I am lost. Ooh. We got this, te to the minus or minus te to s minus st over s plus 1 over s. Wait, where did this 1 over s come from? Oh, from v. Hold on. This needs a 1 over s. So then this is going to be e over s squared. Yeah. Okay. So then we take the integral and we get... Wait, hold on. What? Okay, wait. Here's the... Okay. Hence, we get the integral is... What is this? This is already... Oh. Plus 1 over s. This. so then we're going to get one over s minus t. And this is going to be 1 over s minus t. And then when you evaluate for 0, you're going to get this. So this comes from the 0. All right, so let's try to do it all over again. Knowing that, okay, so the integral, so we need to just figure out, so the final integral is this, which is, so the integral from te to the minus st dt is equal to e to the minus st over s squared minus te to the minus st over s. So now we just need to do this, but we need to, we need to evaluate this at b and 0 with limit as b goes to infinity. Okay, so the next step then is let's just replace this for t for b. So we're gonna get the first part is e to the minus s times 0 over s squared minus b times e to the, wait, are we doing 0? Or we do the 0 part first. So this becomes 0. So then this all is 0. So this cancels. So this is at b equal to 0. Or t equal to 0, however you say it. Now we want to evaluate e to the minus st over s squared minus te to the s minus st over s for b. And this is going to be e to the minus sb over s squared minus be to the minus sb over s lim as b goes to infinity. So what we have to do here, so this is going to go to 0, right? Then this is going to go to, this one goes to 0 because of the L'Hopital's rule thing. Because you get b over s e to the sb, and then you take the derivative and you get 1 over s squared e to the sb. And then this goes to infinity, so this goes to infinity. So this whole thing goes to 0. So then this whole thing goes to 0, right? So then all you're left with is 1 over s squared. So all that's left is L of t is equal to 1 over s squared. All right, and if we look up at that table, because they said there was a table in the book. I don't know where it is. Dude, they really want you to do this? Okay. T to the 5th? Dude, imagine doing 5 integration by parts, bro. All right, let's do problem 7 now. Let's do an inverse Laplace transform. Let's find L inverse of 1 over S minus 3. Now, I don't even remember how we're supposed to do this. How do you do it? You have to remember the rule, right? So you remember the rule that for 1 over S minus A, did they give us that? Yeah. So we remember that L of e to the AT is equal to 1 over S minus A. S greater than A. So then if this, then this is going to be y of t is equal to e to the 3t. Okay, so our for problem 7, our answer should just be e to the 3t. Cool. Yeah, if you don't remember this one, it's like, come on, you got to remember that one. No, but we need to specify t greater than or equal to 0. Okay, let's do problem 8. Okay, so this one they're trying to get you to recognize the inverse Laplace is a linear thing, so you can take out this constant of 5/3 and then just figure out what the inverse Laplace of 1 over S is. 1 over S is just e to the t. So I think for number 8 we should get L inverse of 5/3 5 over 3s is going to be equal to 5 over 3 times e to the t. Oh, because no. Yeah, because a is 0. A is 0. Because this would be 1 over s minus 0 is equal to e to the 0t. So then you get, so L inverse of 5 over 3s is just equal to 5 over 3. All right, that's pretty cool. Number 9. I think you could just write that as no, I don't know. How do you do number 9? L inverse of 2 over 3s plus 5. If you factor out a 1/3, so you get 1/3 times 2 over s plus 5 over 3. Then, wait, but the 2 on top might actually mess with me. So if I pull out a 2/3, and this is a 1, we're going to get 2/3 e to the minus 5/3 t. All right, I think I got that. I think I got that one for real. Yeah, I said 2/3 e to the minus 5/3 t, but that's the same thing. Nice. All right, do we want to solve some IVPs? I feel like we should just go on to 6.2 just to read it, and then we'll do some more problems later. But we did like, I don't know, 5 problems or so. We didn't do any IVPs though, which is sticking it all together. All right, we'll do problem 15. Another time. Another time. That's it.